So now let's have a look at the laminar flow case. So in the previous video we looked at this case, which was the Stokes flow case, and in this case we used this kind of an FEM discretization, right, for our continuity equation and our Stokes flow. And we looked at P1 element, and this pair is not stable. It doesn't satisfy the inf sub or LBB condition, and so to stabilize this we have to add a stabilization term, and this was our PSPG term, which is an element level integral. And in this case you are just multiplying grad q, which is where q is your pressure test function. So you are just dotting it with your residual, and you are integrating inside the element. So for the Stokes flow case, you just have these two terms, right, and this is a second order derivative. So for the P1 case, this just goes to 0, and this guy will only appear in your residual if you are using your convective term. So now let's just do that. Let's add the convective term, which is this term u dot del u, into your velocity. So this makes this into the Navier-Stokes equations, and now these are non-linear. So this guy was adding a very symmetric contribution. So in our matrix structure, A matrix was very symmetric and very nice. We could just solve it very easily. It was a very easy problem to solve, because in Stokes flow we had a symmetric kind of term here. Now to this term we are also adding this guy, which is not symmetric, and this will make the equations more and more hyperbolic as this term starts becoming more and more dominant, right? So for this term we have to add upwinding, which is what SUPG does. And so SUPG is added to your A matrix and your B transpose matrix, which means it is being added to basically your Navier-Stokes equations, and your PSPG term is being added to your continuity equation and your null matrix. So in case of Stokes flow, PSPG was only being added to the null matrix because this guy was going to 0. You had no u dot del u term, but now that you have this term, PSPG will also be added here. So the net effect of these additions is that this entire system is going to become more and more symmetric, and so inverting this matrix is going to be really easy. So to give this intuition, I have really used a stiffness matrix approach, but you could do this in a Jacobian as well. And in fact, when you use a Newton-Raphson kind of iteration, once you do all of this stabilization, it converges really fast. You will just converge like maybe in 3 to 6 steps for every iteration, very fast convergence. Whereas in this case, I am using a stiffness matrix approach, which along with a Picard iteration, which is slow, but really the idea is to understand what's going on. And so to keep this as a tutorial kind of structure, I have just kept this as a stiffness matrix term instead of a Jacobian. So this will solve fairly slowly as we increase the Reynolds number, but I think from a walkthrough point of view, I think this is very easy to understand. If you write the Jacobian, you will just have some really long terms coming here. So let's just understand what is SUPG first, and then we can look at what's happening in the code. But to motivate that, we can just solve our lid-driven cavity problem once again without PSPG, and let's see the kind of accuracy we get. So we'll run this problem at Reynolds number is equal to 10,000, and we have a very famous paper, Ghia et al., which is very well known. So we'll grab the readings of Reynolds number equal to 0. We'll only look at really one variable, center line x velocity. So there are so many things that you can verify, but let's just look at center line x velocity, and we'll plot this in paraview. So let's just do that comparison, and let's see how a pure PSPG approach functions. So in this case, so this is our matrix, our stiffness matrix assembly, and at the beginning you have your PSPG and SUPG parameter or multiplier calculation, right? So as I've shown here, you have your tau parameter here, so which is basically just scaling your SUPG or PSPG terms. So So really these are different for SUPG and PSPG, but in this case, to keep it very simple, I have just for demonstration it is okay to just keep both of them the same. So I have just maintained them with the same kind of formula, right? This one. And in this code we can just turn them off as we want. So right now we'll just turn off SUPG and we'll keep PSPG on. Okay, so because without PSPG we'll not get a convergence. So let's just run this code at Reynolds number equal to 10,000. So here I am just doing this mu as I have just reduced the value of your viscosity, so that just works as the same way, in the same way. So now we have Reynolds number equal to 10,000, and let's try solving this. And this will converge really slowly because this is the Picard iteration, and with the Newton iteration this will happen very fast. But of course Newton will not converge immediately if you have a 10,000 Reynolds number directly. So you would have to use some pseudo time stepping or probably march in Reynolds number, some good initial value, and this will just converge in 3 to 6 iterations. So maybe just in a few seconds you will get the result. But right now we are trying to understand from an understanding point of view. This is very simple to understand. So let's look at where the convection terms have been added. So this is your A matrix, local A matrix assembly, right? And so you had just your viscous terms. So now you also have your convection terms here, which are added where your del square u is being added, right? Basically to your xx and yy terms inside it. And so now you can see these are your convective terms, and you can see that this is your shape function, which is basically your test function, right? So the test function transpose, and you are hitting it with this guy, which is basically your trial function, and we have again written it as an outer product, right? Very similar way. And let's look at what is this A. So A is just your velocity. We have also shown this, I think, in the previous video. So this is just your shape function dotted with your velocity. So these u1 element are basically, they are the velocities inside your element. It's a vector of values. So if you have a p1 matrix, they are just your 3 values inside the element. It's a straight 1 by 3 vector. It is multiplied with this shape function, which are just your psi, eta, and 1 minus psi minus eta calculated at the Gauss points. So you are just dotting this and you get a scalar value out of this, and this is basically being multiplied with your del u, right? So you have your u dot del u here. So these are your convective parts, and after adding that we have your SUPG parts, but right now we are not adding them. We have turned this to 0, so let's ignore this. And rest nothing changes as far as a pure convection or laminar case is concerned. So we have our SUPG. Okay, of course you have your SUPG term, so sorry, PSPG term, in which of course you are seeing this addition here, right? So we already talked about this. So there is this guy u dot del u appearing in the residual. So this will get dotted with your grad q and with your tau PSPG. So now you can see that inside your continuity terms for this B matrix, now you're seeing PSPG being added. So that's the change, along with addition of your convective terms, right? So that's the only change, and by doing that we have got the solution. So let's have a look at the solution. So this is just your vortex. This is your lid driven cavity. So really we won't understand anything unless we actually plot this on ParaView. So let's just plot this, and there is a ParaView export option in the code which I am attaching. So it writes a .vtp file here. So let's just upload this. So this is our solution for x velocity, and let's just add a filter, plot over line. So we are just interested in the center line x velocity. So as you can see, this is the plot, and here you have your, on this side you have your lid, right? So this is y coordinate equal to 0, and this, so maybe I can just write it down. X velocity at center line, and this is y coordinate at center line. So at y equal to 1, so this is y equal to 0, so this is the bottom, and at y equal to 1 we have a velocity of 1, which is your lid, right? So you have a sharp gradient here, and this is your solution. So now let's remove this so that we can see this more correctly. And now let's grab our data, so which I have also provided in this CSV file. So we can just read this and apply this. So right, so let's just remove all of them. Let's just keep the Reynolds number equal to 10,000. So this is the Reynolds number equal to 10,000, so let's just put it as data points so it becomes more visible. Right, so this is your solution, and as you can see there are some oscillations here. So this could also happen due to the grid, right? But you can see that the solution doesn't fit well. So you could try to really make the grid finer, and this would converge, but really the idea is not to make the grid finer. We need SUPG and PSPG because we want to make the grid, we want to use as coarse a grid as possible while getting the correct approximation. So let's just try this out with SUPG and let's see what happens. So before this we have to understand what is SUPG. So this has already been explained actually in the previous sessions in the 1D case, where we looked at a very simple convection diffusion problem, a scalar transport equation. So I think I'll just revise that a bit, and that case is pretty instructive. So in the scalar transport equation, so let's just write a scalar transport equation for our concentration, for example. So let us say we have this kind of an equation, and we are solving this equation in x equal to 0 to x equal to 1, and at x equal to 1 we have u equal to 0 as the boundary condition. At x equal to 0 we have u is equal to 1. Okay, so we have a curve like this, right? Something like a boundary layer here, and as this term starts becoming more and more prominent, so you could have, for example, a k here, and if your characteristic length, in this case let's say it is just 1, L is equal to 1, so you have your parameter UL by D in this case, which is your, or K in this case, UL by K, which is your Peclet number, right? So your velocity into your characteristic length divided by your diffusivity, that's your Peclet number, and this is showing the effects of the convection to your diffusion. So as this term becomes higher and higher, your convection is becoming more and more prominent, which means your equation is becoming more and more hyperbolic. And since finite elements, Galerkin's, since Galerkin's works more like a center difference scheme, if you try to increase the Peclet number, even like if you try to make it 10 or 20, 25, so you will start seeing oscillations here, right? And we saw this, all of this on an Excel sheet actually, and we also built an Excel sheet for SUPG, and we looked at how with SUPG you get nodally accurate values even at Peclet numbers like 10,000, or you could really just crank up the Peclet number to any value you want, but you would get nodally accurate values. So let's motivate that concept a bit. So let's say if you have this 1D case in which let us say you have these 3 elements, and you have, maybe I'm really bad at drawing. So you have your linear hat kind of functions over 3 elements, right? So let us say 1, 2, 3, 4, and you have some values here. Let us say C1, C2, C3, C4, okay? And let us say these functions are basically psi, we call them as psi, which are your test or trial functions, which are simply your linear hats. So in the Galerkin's case, if we are really discretizing this guy, which is your diffusive term, so if we were to write our stiffness matrix terms, so let's write down a local stiffness matrix, K11, K12, K21, K22 of the first element, and K22 of the second element here, plus, so this is K23, K32, K33 of the first element added to K33 of the, of the second element added to K33 of the third element, and so on. So let me just complete this. So this is K34, K43, K44, and rest of the terms are just zeros. So when we are discretizing for this term, which is your diffusive term, you get a stiffness matrix K, which is a diagonally dominant matrix. So it is diagonally dominant, it is also symmetric. In most cases it is actually SPD, so it is symmetric positive definite kind of matrix, which means that the eigenvalues you will get are definitely positive values. So it's a very well behaved matrix which you can use very easily. You can invert it very easily and get the solutions. But when you have a case where this convective term is becoming more important, in that case these guys here, the diagonal ones, these guys, so they would just become close to 0. So if you were looking at K21, K23, so they might be of order of, let's say, 1 or 1 e raised to minus 1. So I'm just putting some dummy values. So we actually had an Excel sheet where you could see this happening. So you could go to the previous video and you could check it out. So there's an Excel sheet and you will see this exactly working out. So these are just dummy values. But if you are looking at K22 plus K22 for your convection case, you might have something like 1 e raised to 8, something which is very close to 0. Okay, so which means that when you are multiplying this K matrix with your velocity, I'm sorry, not your velocity. So in case of Navier-Stokes, it's your velocity. In this case, it is just your concentration, right? So these concentrations are basically just these guys here. So if this, let's look at node 2. So if this guy is going to 0, this means that the C2 value, which would appear here, C1, C2, C3, C4. So this C2 would go and match with this guy here, right? So C2 is not very, so if this term K22 plus K22 is almost 0, So this means that C2 is not really well identified with the node 2. But C2 is well identified with this guy. It is also well identified with this guy, which means that it is well identified with these nodes, but it is not well identified with its own node actually. So the solver tries to approximate the value of C2 based on the values of 1 and 3, and it will just oscillate, and it will never converge. That is because this is a central difference kind of approximation. And so to solve this, you have your SUPG stabilization. And in SUPG stabilization, what you do is that you just take the gradient of your trial function, you project it along the direction of your velocity, and this becomes your test function for your Petrov Galerkin method, which means just as before, for your SUPG case, we multiply it with the residual, which is again a strong form, residual strong form, and you integrate over the element. So this is again an element level integration, and this will be multiplied by a tau SUPG, very similar to your PSPG. But what's happening here? So if your residual in this case is basically u dot del C minus k into del square C. So this is your residual in the 1D convection diffusion case, and this is your test function, right? So C can be discretized again and just as a linear combination of your trial functions, and you would again get something like this, u dot del psi. So every term inside your stiffness matrix would be something like this. So if you are using linear hats or linear functions, this guy just goes to 0 because it's a second order derivative and it's a strong form, so we cannot take integration by parts. So this will just go to 0 and you are just left with this, which means that you are basically just having this kind of a term which is perfectly symmetric. So you are just projecting this guy onto this trial function onto this test function, right? So so this is very symmetric, unlike your case when you used a center difference kind of approximation, a purely Galerkin route. So in that case the matrix had zeros on the diagonals, but now you don't, because you are really working along the streamline direction, right? Because this test function is testing along the streamline direction, right? So this leads to diagonally dominant matrices, and this is also called as streamline diffusion method, streamline diffusion, or streamline diffuse. No, I've never heard it as streamline diffused Petrov Galerkin. I have always heard it as streamline upwind Petrov Galerkin, or as a streamline diffusion method. Both are really the same. But really the idea is that you are having this kind of a term which gives you a diagonally dominant matrix and a symmetric matrix, and you add it to this guy, right? The pure diffusive part. Of course, when your Peclet number is really high, this term is almost 0. It's very small contribution, but it will be there. So that is how you stabilize your 1D convection diffusion equation. And if you want to have a look at how each matrix looks, how locally or globally, so you could just go to the previous video, and I leave a link in the description, and that should make it clear. So in case of our Navier-Stokes, we are just going to do the very same thing. So in case of our Navier-Stokes, we will just again be doing something similar to this. So we'll have a tau SUPG, with u dot del v. So let's write this for our x velocity first. So this is the test function, right, for your x velocity, or your x momentum balance to be more accurate. And you have your right, so this is your x velocity, right, your x velocity momentum part, right, and this residual also will identically drive to 0 as your solution is being satisfied iteratively. And so this is again a consistent stabilization, and you would do the same for your y part as well. I'll not write it down, but I think that's pretty straightforward. So you can see that SUPG terms are being added to the A matrix, which means this part and this part, and also to this guy, which is your gradient of pressure, right? So this is about your SUPG. Now let's see where these terms are added. Before that, maybe we can just start solving by using SUPG. So let's just turn it on. So we are using the same value which we use for PSPG, right? So we'll allow this to run, and this will just be slightly faster, I guess, but not much difference because this is again a Picard iteration. So in the meanwhile, let us have a look at where this SUPG is being added. Again, you can see in the convective terms, you're adding this guy. And this is very easy to understand in the stiffness matrix format, because you just have this term multiplied by this transpose, right? This very simple vectorized kind of form. And SUPG could also be added to your P2 P1 formulation. So after we are done with this, I'll also show you the results for a P2 and P1 formulation, though I will not really run this solver again. I'll provide this file, and in this file you can see grids of different refinement are also available. So this is almost close to completion, so let's have a look at how the SUPG solution differs from PSPG. So let's put this as a dash. So this is our PSPG solution. So now let's just use our SUPG solution. So you will not see much difference in the graphs here. So let's just plot this, and the difference should become clearer. Right. Right, so now you can see this is your SUPG line. Maybe I can just put a different color so that it becomes more clearer. So this is SUPG plus PSPG for P1, P1. Right. Now you can see that it is somewhat more representative, at least till it reaches this point. And in fact, it is quite more accurate as compared to your PSPG. And really the idea is that we want to use as coarse a mesh as possible and get these solutions. Of course, in both of these cases, if you just keep refining the mesh, both of these are consistent stabilizations and they would just converge to the same data, right? So really you can see that the PSPG kind of stabilization is, the SUPG kind of stabilization is more accurate. It is giving more accuracy to your PSPG stabilization. Of course, these are very small grids because you are just having 6,000 DOFs here, right? So if you so let's see what happens when you have 30,000 DOFs. So and I have also shown the comparison here with the P2 P1 case, and then it will become, I think, much more visible. So right. So this is the comparison for a data which is having almost 30 to 35,000 DOFs, and let's compare this. So so here your dashed data is basically your P2 P1 unstabilized with 35,000 DOFs, right? So this is purely P2 P1 function, right? This dotted line, this green line is your PSPG and SUPG for P1 P1. So you can see that even P1 P1 elements are more accurate than your P2 P1 elements after you have applied SUPG. And this guy here, which is more representative. So this is your P2 P1 along with SUPG, and this you will see for most of your test cases in laminar incompressible cases. So adding SUPG really makes your simulations more accurate. So if you are looking at the lift coefficient or the drag coefficient for your flow past a cylinder benchmark, so even in that case, when you have SUPG, your drag or lift value is more accurate. But you have to use the formula for SUPG from the literature. So if you overshoot the stabilization parameter, then of course the solution will become over stabilized, and really you will get very wrong values. So one has to be sure. So there is a small there is really a small change that we can do here. So for example, this is your arbitrary parameter. So the recommended values are 3 to 4. So you shouldn't really take it to 10 or 100, or I mean, you can't just put any arbitrary values. So you just have to use the values from the literature, and there is so much literature. So stabilization is almost like an art. So actually it's a science, of course. So there are so many papers on this, and you could read them and stabilize your solutions. So of course for the P2 P1 kind of stabilization, the method is slightly different. So I have still used for this case, I have still used P2 P1 method, which is really same as this one. But really, if you want to make a good use of stabilization, you have to go to the literature and have a look, or you have to derive it theoretically. So this is what I wanted to talk about, the SUPG stabilization, and hopefully I will attach this this bunch of code, and hopefully for somebody who is just starting off with finite elements and CFD, this will be a useful walkthrough. So I'll end this video here, and in the next case maybe we'll just touch upon a very simple turbulent flow case, and we'll just leave it at that. I hope I'll be able to also keep making videos on this and deal with some more advanced topics after this. So I thank you, and I'll take my leave here, and I'll see you again in the very small video after this.